I'm Mike Eastham. I'm here to talk about our experiences building a unified feature platform with DuckDB and Arrow. And I'll just get it out of the way right now. I don't have any quarters on me, so I'm not going to be able to fill the tip jar every time I mention Arrow in this talk, but I'll sort something out later. So here's some biographical information about our company. Our founders were from this team at Uber called the Michelangelo AI platform. They were some of the first people to popularize the term feature store, which some of you may have heard of. And so that's a concept that we've kind of like deeply embedded in our product at Tecton. We've been around since late 2018. We're now about 45 engineers. And this is kind of like our mission statement here. We build a data platform for production machine learning applications. And I always, like, at least from a technical perspective, the word I focus most on in this sentence is production. So a lot of our goals and like the trade-offs we make are really focusing on people that are building production ML systems. And what I mean by production is cases where you have like an end user waiting for the result of your model. And so things like availability and latency are extremely important in the systems that our users are building on top of Tecton. Building these types of systems involves solving a lot of really challenging data problems. This is a slide I've stolen from our lovely marketing team that talks about all the different problems you might run into. A lot of these are pretty standard, like almost all of you have run into things like this, I'm sure, building any sort of data pipeline for any sort of use case. There are a few things that I think are kind of more specific to the machine learning use cases that we're serving. Particularly on the left side here, we have kind of all of these different scenarios where you're defining features in different contexts. And we found that with a lot of people, if they aren't kind of taking a organized approach to this, you can end up in this situation where you have the definitions of the features that feed your machine learning models. You'll end up with like maybe sometimes 3 or 4 different definitions throughout your company or throughout your system. So kind of a classic example of this would be you might start out, a data scientist might start out building and experimenting with features inside like a Jupyter notebook. They might have some pandas or SQL code in there, and then they use that to train their model. And then later on, they'll take that notebook, kind of throw it over a wall to like a server team, and then they re-implement some of those features inside the server code. And when you do things like that, you end up with like mismatches between how you train the model and how you're actually serving it. And those types of scenarios can really tank model performance. And then some of the other like somewhat unique things to our use case are over on the right side of this diagram, like all the serving stuff. Like I mentioned, like we want to solve these problems in a way that allows us to support serving machine learning models with like really high availability and latency guarantees. So these are some of the things we're trying to solve. How does our product approach this? So kind of the central thing we do is we provide a declarative framework where our users, who are data scientists, data engineers, ML engineers, whatever you want to call them, they can define the transformations that they want from their raw data sources into the features that they want to put into their machine learning models. And they do this in one central place. And then from this definition, we orchestrate some pipelines that implement those transformations in a few different contexts. So one of those would be running them over large batches of historical data. That might be if you're developing a new model and you need to backfill feature values for the features that you're defining. And then there's also kind of like the ongoing case where maybe you've already put something into production, you need to be refreshing those feature values on an ongoing basis. And maybe you need to either do that in batches, say maybe your data sources are files in S3 or something like that, logs coming from your production system potentially. Or sometimes you want to do that on streaming sources, say if you have a system where like the freshness of the data going into your model is very important. So we orchestrate pipelines to cover all these cases, and then those pipelines feed into storage system, which is what you could call the feature store. And from that feature store, we need to be able to serve 2 different types of queries with like kind of different performance characteristics. So the first type of query we call offline queries. These are typically for generating training data for training a model. You run these in batches, and each like item in the batch or each row in the batch is for a given entity and also a timestamp. So if you're training your model on like labeled events that happened in the past, you need to make sure that the feature values that you're retrieving for those labeled events are at the correct time in the past and not like the current value of the feature. Otherwise, your training will be wrong. And these types of queries we want to optimize for throughput. And then for the other type of query that we have are online queries. And each of those is only for a specific entity key. You can't specify the timestamp. It's kind of implicitly the most recent data that's available. And these are the types of queries that you would use when you're actually trying to do inference with your model in production. And so having a single declarative feature definition is really important for satisfying all these use cases. It kind of solves the problem that I was talking about earlier, where you might have like, the notebook version of your feature and then the production version of your feature. Eliminates a lot of those potential sources of skew between your training data and your serving data. It also lets us kind of handle a lot of details of pipeline management on behalf of our users. Let them focus more on what they're actually, the problem they're actually trying to solve, which is to, define training data for their ML models and kind of worry less about setting up, like distributed cron jobs or whatever else they may be doing. We also try to use this framework to enable experimentation. So we provide, a mode for our framework where people can run it in a notebook and experiment with feature definitions in the framework without having to wait on, big batch jobs to run or anything like that. So we want to really enable people to experiment and iterate on their feature definitions quickly and then be able to put those in production without having to rewrite anything. And then additionally, having these uniform feature definitions forms the basis for a lot of the other functionality of our product. This is not really the focus of my talk, but I'll just mention it right here. So it lets us do things like monitoring, governance, lineage, feature sharing and reuse, all that good stuff. So that was all pretty kind of abstract. So how does this stuff actually look in practice? This is how kind of data flows through the system. On the left, you see some example types of data sources you might have. Data goes through all these transformation steps in the middle. And then on the right side, you can see the databases that make up the feature store. So in our case, we actually just split this into two different database systems. On the top, we have the online store, which serves the online queries. We support a couple or three actually different databases for this. Could be Redis, Dynamo, or Bigtable. And then below that, we have the offline side of things. That's a DeltaLake table in usually in S3 for us. And the offline store is what serves the offline queries or offline retrieval. To make this concrete, I hope this is legible to people in the back of the room. I have some kind of example data that you would see for a click prediction use case. So on the left, we have the data source, which is just a super simple log of clicks that you might get from a web server or something like that. It's got an item ID column, which is the item that's been clicked on. It's got a timestamp when the click happened. After that goes through this whole filter, transform, aggregate pipeline, what comes out is sort of these 1 hour binned sum of clicks on a given item. You can see here the timestamps are aligned to the hour. And that's what we end up storing in the online storage and the offline storage. So for the data in the online store, that's picked up for our online serving system. That's also kind of out of the scope of this talk. But when you want to do offline retrieval on this, you will pass into the offline retrieval job a list of items and a list of timestamps for which you want to retrieve feature values. In reality, you might also have other additional metadata associated with this, but I want to keep this simple. And then what we return from that, in this example, I have a 1 hour sum and a 2 hour sum of clicks as of the timestamps that are passed in. And this shows kind of one of the nice features that we've implemented here, where you can have in the storage, we just have these 1 hour bin sums of clicks, but then we can extend those to larger time windows, which is something that people frequently ask for features in their ML models. They want to do a 1 hour sum, 6 hour sum, 12 hour sum, and have all those as separate features. So historically, we built the product all around Apache Spark. So all this stuff was implemented as two separate Spark queries. The first one we call the materialization query. This is run periodically or sometimes as a streaming job. And that's kind of continuously populating the storage as the data sources are updated. And then separately, we'll have a retrieval query, and this is what's run on demand by data scientists either when they're trying to generate training data sets, or maybe if they want to do a big batch of like weekly predictions from their model or something like that. And so that's run as a separate Spark query. To facilitate like iteration and experimentation, which is one of the things I talked about, we also have a way of just merging these together, cutting out the storage in the middle, and just kind of running it all end to end all in one go. And that's what you might do when you're running this in like a notebook, trying to develop new features. So some details of like how our customers end up interfacing with Spark. So they actually have to write like PySpark and Spark SQL transformations themselves inside of our framework to make all this work, because we need to be able to drop their transformations into these Spark queries. We take those Spark queries that they send us and we combine it with a library of like common Spark query behavior that we have. That includes things like filtering out timestamps to the relevant time range, implementing those incremental aggregations that I was talking about before, and then also like all the stuff for handling how we format things to write into the feature store. And then we take these combined jobs and deploy them in the user Spark environment. So that would be something like Databricks, EMR, or Dataproc. And an important point here is that like we have to have customers control most of the configuration of these jobs, because they're writing the transformations, they're the ones that know the shape of the data, and so they're really the only ones that can have all the information in order to size the jobs and like set the configurations properly. But this has caused a lot of problems for us historically. One of them is just that like people find Spark very confusing, particularly if they haven't used it before. I have an example here. I just like searched for Spark error on Stack Overflow, and this is one of the first things that came up. This isn't actually the whole thing. There's like another slide, and then it actually like, I don't know if you can read it at the bottom there, but it says there's 76 more stack frames that didn't fit in the error message. So this is pretty confusing. I think like a lot of people run into this and they're like, what does this mean? Some of you might be saying, okay, this is a trick question. I can just like put it into ChatGPT and it'll tell me what happened. And like in this case, it actually, this is much better than what we had before, but I think a lot of people that are just trying to train an ML model are gonna, not really know or care what a no such method error is, or what a Sedona conf is, or like where they would find it, or how to fix this. So we find that a lot of our users, like when they run into this stuff, just like very often get stuck and need to ask us for help. So yeah, like we have this principle in our product. I think most people building products have a principle like this. Like we don't want our users to get stuck on errors. Like we want there to always be a path forward when they're running into issues. But we found that by like deeply embedding Spark in our application, we're not really able to like satisfy this principle, because there's this huge surface area of errors that can occur in Spark. We can't predict them all, and so we're not really able to like, help our users when they run into problems. So this isn't a great situation. Another kind of example of one of the problems Spark causes for our users. This is the table of contents for the page in the Spark documentation that has all of the configuration parameters for Spark. I think there's like 500 in total or something like this. People obviously like don't want to learn all of this stuff, but it's actually pretty important to know which of these might affect your job, because with Spark, there's a lot of configuration parameters that can like dramatically impact the performance or even the correctness of your job. And so it takes a lot of kind of like battle experience to figure out which pieces of this you need to read in order to be successful. And then another issue, like Spark complicates deployments for us. I mentioned before, we require a managed Spark environment for our customers to use our product. This really slows things up if people haven't been using Spark before. Sometimes involves like a third-party vendor that has to get involved when we're doing deployments. Nobody really likes this. And then final problem here with Spark, like I've said here, it's heavyweight. What I really mean with that is that it doesn't like scale down well to smaller use cases. So like if you want to just run a query on a small subset of data on your laptop, like maybe in an experimentation use case, you still have to worry about setting up a Spark master. That's done differently than you set up production Spark jobs. You need to make sure you have a JVM on your system. Sometimes you need to go hunt down jars for data sources. It's not really like a fun experience. And then additionally, like with Spark, we run separate Spark clusters every time we do these materialization queries. Those can sometimes take like 10 plus minutes to start up. And depending on how much data you're dealing with, you might actually end up spending more time waiting for the cluster to start than you're actually doing processing data. So that's like not very fun for anybody. So I bring up all this not to really trash Spark. I mean, Spark is really, capable of a lot of very impressive things. I think the conclusion to draw is just that you need to choose the right tool for the problem you actually have. And for a lot of our users, they're not dealing with the kinds of massive data sets that warrant this type of complexity. And so I'm not the only person that has, made this observation. I found out after I put this deck together that this blog post actually came from a talk that happened here last year, so some of you may have seen the talk. But yeah, there's this blog post called Big Data is Dead from OtherDuck. It goes a lot more into the types of issues that I was just talking about, and I think kind of as a better articulation of what I was just talking about in the last few slides. So if you'd like some more information on any of this, go check out this blog post. So I've just been, running through all these problems that Spark causes for us in the way we've historically built our product. And, around well, I guess this conversation really started about a year ago. A lot of people in my company, we got together, we identified all these problems in our user experience that are caused by Spark, started trying to figure out if there's something that we could do better. So we started coming up with lists of requirements for what a replacement experience would look like. A big category that we wanted to solve is DevX. So we want people to have the flexibility to express their transformations in the language or framework that they want to use. We don't want to be forcing people to write PySpark or Spark SQL anymore. Oftentimes, we find with our customers at least that people want to write pandas or they want to write SQL maybe in a data warehouse SQL dialect instead of a PySpark SQL dialect. But we really want to be flexible here and just give people the options to do what they want. We want to support a really good local development experience. In particular, in the local development experience that we're most interested in is running our product inside a notebook. And in that type of scenario, we want it to be really fast to start up. We don't want to require people to have complex dependencies already installed on their system, so things like the JVM or Hadoop jars. We really want to just have a pip install and then run it type experience. And then we also want to be able to process non-trivial amounts of data in resource-constrained environments like laptops. We want to solve these problems we have with our Spark deployments. We don't want to require third-party vendors like we have in the past. And we also want to be very frugal with the amount of configuration knobs that we expose to people. So we don't want to force people to have to learn all of this stuff besides their query in order to be able to deploy their pipelines. And then finally, we want to keep all of these integrations with data sources that we've supported in existing versions of the product. So some of the building blocks that we identified that would be useful for building out this type of experience, one is Arrow. You've heard a lot about it at this conference, so I'm not going to go super in depth about what it is, but it's the two important. I think Arrow kind of has a lot of different facets. What I have here is from Arrow's website, explaining kind of the three pillars of what the Arrow project is. For us, the important pieces of it are that it's a format that we can use to kind of glue a lot of different pieces together, make different building blocks of our data pipelines interoperate efficiently together through this common Arrow format. And then also we make a lot of use of the Arrow libraries. So in PyArrow in particular, provides not just the Arrow data types themselves, but it also provides functionality for interacting with common data formats like Parquet. So we make a lot of use out of that. Another building block we've used is DuckDB. You've also probably heard of this, but DuckDB, they describe themselves as a fast in-process analytical database. I think another way to think of it is just the SQLite of analytical queries. And why do we want to use DuckDB? I've kind of broken it down into three categories here. One is that it has really great interoperability with Arrow. This was kind of table stakes for us with how we were building this system. The performance of DuckDB is really great. I think, I don't have any benchmark data here, but I think in lots of cases, it's one of the fastest single node query engines for a lot of the analytical queries that we're implementing. Another nice performance property of DuckDB is that they've done a lot of work to make sure that it can process non-trivial data sets with pretty modest amounts of RAM. They accomplish this through a couple of features. One of them is that they're able to like stream data through a query, so you don't have to materialize the entire input into memory at the same time. And then they also have things like support for spilling aggregation state to disk in order to support aggregation states that might be larger than memory as well. And then finally, like DuckDB is very simple, like usually just works out of the box without any tuning or configuration parameters. So it meets our needs on that front as well. So here's kind of the same diagram we had before. So the kind of logical shape of this is going to look very similar. All of these yellow dotted lines here are places where we've like introduced seams in different components, which end up being, we use Arrow to communicate between the different components. These pieces here we implement with DuckDB, so kind of the filter and aggregation stuff, which is part of our standard query library. We migrated all that to DuckDB SQL so we can run it in DuckDB queries. And then the offline retrieval step where we're like rolling up aggregations to longer time windows and doing this point in time correct join and all that stuff, we've also implemented as DuckDB queries. To get data into the system, one of the things that really kind of enabled us to build things in this way was that a lot of the first-party libraries for all different data warehouses, different types of data source formats, these all support Arrow natively now. So we're able to kind of just pull, without really doing very much work, just include these libraries as dependencies. They'll all give us Arrow data frames, and so a lot of that's taken care of pretty easily. For the transformations, this is basically where we're running the user code. And this is where another place where the ubiquity of Arrow really kind of like enabled us to take this approach, because pretty much any type of interface that you might have for a user transformation function, whether that's DuckDB SQL, whether it's taking pandas in and returning pandas data frames, whether that's doing the same thing with Polar's data frames, pretty much all of those can efficiently and easily be converted back and forth with Arrow. So for this transformation step, we really will just now support anything, any type of data format that can be easily transcoded to Arrow. So we're able to give people a lot of flexibility here. One piece where the solution doesn't fit like cleanly in this diagram is writing to DeltaLake. So normally when you're writing to Delta, you're like running a big Spark job or maybe a Flink query or something like that. It's not immediately obvious how to write into DeltaLake if you just have like an Arrow data frame or a DuckDB table. Our solution to this is a little interesting, but first I think it's good to take a step back and like be like, why do we even have Delta here? Like, why can't we just write Parquet files into the object store? The one word answer for this is like we need atomicity for a few different operations. Particularly like appending time ranges, it's nice to have atomic appends, but it's not super critical. Where we really need it is for operations where we need to like partially delete data within the offline store. This is very common for like GDPR compliance reasons. We might need an interface to wipe out like a certain entity in all of our feature storage. With a naive Parquet table, that involves like reading a Parquet file, deleting part of it, and then writing part of it back. But then you either create like gaps in your data during that process, or you'll have certain rows appearing multiple times. And so having a Delta layer on top of that, which gives you ACID transactions, is important to not be like corrupting people's training data sets when you're doing these types of operations. So if you want to add a DeltaLake integration, like the obvious place to start is just by going to Delta's website and looking at their integration page. They've got a lot of different things here. This Python one at the bottom looks pretty interesting. Like we've written most of the system in Python, so let's see what this is about. If you click that, you actually go to the Delta Rust library, and that's because like so many things these days, the Python library is just like a thin wrapper around the Rust library. So this Delta Rust project is pretty great. I think it's like maybe the only, I'm not sure if this is 100% right, but it seems to be one of the only like independent libraries that's able to like read and write Delta tables. So this is pretty cool. It does a really good job of reading Delta tables into Pyro tables. That all works out of the box, no problem. The issue that we ran into is that it's got pretty limited write functionality. Or actually, I should say it had pretty limited write functionality as of like 6 months ago when we were doing research for this project. I do think some of these things have been fixed already. But in particular, it doesn't support all the write operations we need. It doesn't support things like deleting single rows out of an existing table, for instance. This is a little bit in the weeds, but it's not compatible with Spark's DynamoDB locking protocol. This basically means that if you have a Spark writer and a Delta Rest writer pointed at the same table, you're likely to corrupt the table if they're both writing at the same time. So that's not very good. And then also, since it's in Rust, it uses the AWS Rust SDK, not as mature as the Java SDK or the Python SDK, and it, for instance, like lacks certain authentication options that you'll find in the more mature AWS SDKs. So this can create some problems when you're talking to S3. So this thing like doesn't support the functionality we need. Are we totally stuck? I mean, thankfully not. I probably wouldn't have these slides if we got stuck here. So what did we do? I think it's a little bit helpful to like illustrate what a Delta table actually looks like before we go into our solution. So on the left here, you can see like the file listing of a table called myTable that's in S3. The first couple prefixes, some of you may recognize that that basically looks exactly just like a regular Parquet, like sharded Parquet table on S3. We have a couple different date partitions, and then within each of those date partitions, we have the Parquet files with data for those dates. Pretty standard stuff. The thing that makes it a Delta table is the presence of this additional prefix down here called DeltaLog, and inside there you see some numbered JSON files. And if we look in those files, each of them corresponds to a single Delta transaction. So you can see here the first transaction is like setting some metadata for the table, the schema, the partition columns, things like that. Second transaction is doing the, oh, it looks like my arrows got a little misaligned here, sorry about that. The second transaction is basically just adding some of the Parquet tables to the Delta table. And that's actually pretty simple if you look at how the transaction looks. It's just a list of paths and then some metadata about each file. So pretty simple so far. If you want to modify a file, that's modeled as just deleting the existing file and then adding a modified version to it back. You can do that in one transaction, so everything looks atomic. Pretty simple stuff so far. So the solution we came up with, or actually let me go back to this. So the Parquet piece of this is already pretty easy for us to implement. That's something that like PyArrow supports natively. You just say write Parquet table and it'll do it for you. So to actually get to a complete solution, really all we need to do is figure out a way to write these JSON files. And the solution we found to doing that is there's this thing called Delta Standalone. It's a JVM library, and it's actually part of the upstream Delta project. So I think essentially what they did is they just took the commit writing stuff out of the Spark implementation and then packaged it as a separate standalone JVM library without any of the Spark or Hadoop dependencies or anything like that. It doesn't ever touch any of the data in the table, so it doesn't manage anything to do with the Parquet files. Basically, the way the interface works is you just give it a list of files and then it'll write the transaction for you. So this basically fills in that missing piece in order to be able to write the Delta tables. And so we incorporated this by just like spinning up a little sidecar JVM and then use this Delta Standalone library to write the transaction logs. Running a little low on time, I think I can go through this. So to kind of just illustrate this a little bit further, one of our toughest requirements was to be able to delete a list of keys from an existing table. The way this works with Delta Standalone is you first go to Delta Standalone, you say, hey, give me a list of files in the table. It returns a list of Parquet URLs to you. We load all those as a PyArrow data set. Put that into DuckDB and then basically do an anti-join on it, say like filter out all of these keys that we don't want in there anymore, and then use PyArrow to write that back out to S3 as new files. And then we go to Delta Standalone and we say, okay, delete all these old files, add all these new ones. And then Delta Standalone, it's able to detect if there are any conflicts that happen during that process because it knows the files you read, it knows the files you're deleting, it knows the files you're adding. So it'll tell you if you ran into a failure and you need to retry the whole thing. Otherwise, it writes the JSON file and we're all good. So this is basically the solution we ended up going with. There were a couple different like alternative ways we could have approached this. We could have completely redone all of our offline store stuff into like a different format, like Iceberg or Hootie. We briefly looked into this, but my conclusion was that like the support for standalone writers of these table formats was not really much better than Delta, actually. I think that might change in the future, but at least 6 months ago, it didn't really seem to make sense for us. Another option would be for us to just like improve on Delta Rust, contribute back some contributions and fill these feature gaps. We didn't end up doing that for like time constraint reasons, but in the past 6 months, they've actually filled a lot of these gaps, and so I think this might be something that we seriously look into in the future. Another kind of like interesting aspect of the solution that we came up with is that we have this problem where we have some kind of like esoteric aggregations that we need to support, in particularly the incremental versions of approximate quantile and approximate count distinct. And so to be clear, DuckDB supports approximate quantile, but what we need is actually to like export the internal state of an approximate quantile aggregation. So we needed to implement that as a custom aggregation. Thankfully, DuckDB has an extension mechanism which allows you to add new aggregations. We were able to make this work. However, it's been one of the like kind of more painful pieces of this effort in terms of maintenance. For one, the extension APIs in DuckDB are not super stable so far. We've had to, every time a new minor release comes out, we've had to kind of tweak things, usually tweak the code, definitely recompile all the extensions for the new version. They're about to come out with 1.0 for DuckDB. I don't know if they're planning on stabilizing any of these interfaces or not, but this has been the experience so far. Of course, you need to like compile your extension for every different OS and architecture combination we need to support. That's a little bit of toil there. And then also the built-in distribution mechanism for DuckDB extensions has some issues. You can only publish one version per DuckDB version. So if you have an actual bug in your extension, it becomes, you kind of are like forced to wait until DuckDB releases a new version to fix the bug in your extension, which is a kind of odd setup. But it's pretty early on with this. I'm sure the DuckDB folks are working on improving some of this stuff. And then one final thing I wanted to quickly talk about that this architecture allowed us to do is that we really wanted to support kind of like a deeper integration with some data warehouses. And by that I mean we wanted to like let people write their transforms in Snowflake SQL if they want. And we wanted to be able to actually like push that whole thing down into Snowflake for performance reasons. Because if Snowflake knows about all of the like filtering steps at the same time as doing the transformations, it can often be a lot faster than trying to like download all the data and then us filter it and then transform it. And because all of the DuckDB steps we had were written in pretty standard SQL, and because we have these standard arrow interfaces in between everything, this actually became a pretty easy change for us to make. We basically just pushed the filter step into the Snowflake query, combined it with the transformation Snowflake SQL query, and then everything after this one arrow seam before the aggregate box looks exactly the same. So this is a pretty nice outcome of us going with this architecture. We're able to be like pretty flexible with what we let customers do here. So what are the results of this like new version of the product so far? So we released it in private preview in January, along with some additional streaming ingest functionality that's kind of meant to work together with it that I just didn't talk about in this talk because I didn't have time. Together with the streaming functionality, we've called this new compute engine Rift. It's kind of like the marketing name for it. Our private preview has had a mix of like new customers who've never used Spark before, sometimes some existing customers who were on Spark but weren't happy with it and wanted to try out something else, and also some new prospects that were never customers of ours before. Our hypothesis about this setup being easier to deploy and faster to production than Spark has been borne out so far. I mean, it's a pretty small number of examples, but we found people getting into production much faster than we saw with Spark historically. And then I also have some performance numbers. I want to, preface this. This is not like a super scientific benchmark. I'm not saying that we're faster than Spark in like all cases or even a majority of cases. But for a kind of like representative workload, we found that Rifts, which is what I've been talking about this whole time, actually is able to outperform Spark on like an equal cost basis. So in this bar chart, we basically got three bars for each benchmark scenario. We've got Spark on the left, and then the Rift 2x large is like the equal cost scenario to Spark, and Rift x large would be half the cost of the Spark scenario. So this is pretty encouraging. Like on a 2 gigabyte data set, you can see that even in the half cost Rift scenario, we're significantly beating Spark in terms of the query execution times. And I particularly like in the middle group, we actually, in some cases, like the whole query completes on our system before like Spark even starts up, which is the blue part of the graph. So I think that's pretty nice. Similar benchmark, larger data set. This one's 9 gigabytes. Obviously, this is not like big data, quote unquote, but that's kind of the point in the way, because these data sets are sort of representative of what a lot of our customers are processing. And so in this larger scale scenario, the difference to Spark is not as big, but we're still consistently beating Spark. So this is pretty nice. And that's all the content I had prepared.